Hello, everyone, and welcome to section 8.1, linear differential equations. Now, in this course, or in this portion of the course, we're going to start looking at higher order differential equations. So they're going to be differential equations that look something like this. They're all going to be linear. Okay, so notationally speaking, y prime is dy dx, you know that, but we'll also look at it as dy. So when you look at something like y triple prime or y double prime, we're going to think of it as d cubed y, d squared y. So if you look at the differential equation above, you can rewrite that as d cubed y minus 4d squared y plus 5dy minus 7y is equal to the sine of x, and take out a y, and what do you see? You see something that looks like a polynomial, okay? It's not a polynomial, but it looks like one, and we're going to treat it like one too, but you'll see that as time goes on. First theorem that we look at, very important theorem, says that every solution that solves the differential equation, here it's important that you recognize this form. It's a naught y to the nth derivative. Okay, so the nth derivative y plus a1 y to the n minus 1 plus so on down equals f of x. Every solution to that differential equation is of the form y of x equals y complement of x plus y particular solution of x. Okay, so this is the complementary solution, y sub c of x, and this is y sub p of x. Y sub c of x is the solution to the same differential equation, but not equal to f of x, but equal to 0. Now, keep in mind here, and almost exclusively, the problems that we're going to be looking at for the rest of the quarter is going to be a scalar times some derivative of y. Okay, so scalar times the nth derivative of y plus scalar times the n minus first derivative of y plus scalar times the first derivative of y plus scalar times the 0th derivative of y. Okay, so really get familiar with that format here for the rest of the quarter. So, looking at the example of the theorem above, if we had y double prime minus 2y prime minus 15y is equal to 18e to the 6x. The solution to that, and you're going to take my word for it, this is the solution to it, looks like c1 e to the negative 3x plus c2 e to the 5x plus 2e to the 6x. Now what's underlined here is going to be the solution to the homogeneous differential equation y double prime minus 2y prime minus 15y equals 0. Not 18e to the 6x, but 0. And the particular solution, 2e to the 6x, is the last half of the solution to the differential equation. Now, there's two parts of this. Okay, how do we find the complementary solution? And then how do we find the particular solution? Well, first off, we'll find the complementary solution next section, and then we'll find the particular solution in 8.3. Now, what we're doing here is analogous to our work with matrices. Okay, so if I give you the matrix equation AX equals B, okay, where A is this 2 by 4 matrix and B is this 2 by 1 vector. Okay, when we look at all solutions to this equation, okay, now you can see I already have it in row reduced echelon form. Okay, pivot there, no other pivots here. So we have two free variables, that's x4 and x2. So we say x2 is equal to itself, x4 is equal to itself, x3 is equal to 5 times x4 plus negative 6. Okay, and x1 is going to be equal to 2 minus 3x2 minus 4x4. Okay, and if we look at rewriting the solution, we have x1, x2, x3, x4 is 2, 0, negative 6, 0. Okay, so what I'm doing is I'm picking up all of the parts that are not multiplied by x2 or x4. Add that to x2 times negative 3, 1, 0, 0. And those are all the coefficients that are multiplied by x2. And x4 times negative 4, 0, 5, 1. And so the solution kind of takes the same form as what was on the previous page. Okay, here, this is acting as your complementary solution. Okay, it's the solution to the equation ax equals 0. So had there been zeros here and not 2, negative 6, this would have been your solution, the homogeneous system. Okay, and this right here is acting as your particular solution. It's the fact that this is 2, negative 6. Okay, so there's a nice relationship between the solving differential equations of higher orders, which is what we're now going to do, and solutions to the matrices. So, in any event, just to summarize this, you see that the solution to ax equals b is a particular solution. Okay, so that's pertains to the non-homogeneous part. As this changes, the particular solution changes. Plus the general solution to the homogeneous system. Okay, and that's the same equation, but with 0 here instead of 2, negative 6. Okay, so that's just a quick overview of section 8.1. We'll get started in 8.2 briefly.